The quest for predictability, physics, and the universe. Physics seeks to understand the universe. It aims to explain how things work. At the heart of this quest is the desire to predict. We want to know what will happen next. From the motion of planets to the behavior of atoms, physics strives to make sense of the patterns around us. This quest for predictability has led to incredible discoveries. It has shaped our understanding of the cosmos and our place within it. Imagine a world without predictions. We couldn't trust bridges to hold. Weather forecasts would be impossible. The very foundations of engineering and technology rely on our ability to predict. Physics provides the tools for these predictions. It gives us a framework to understand the fundamental laws governing the universe. Predictions can be simple or incredibly complex. Sometimes we can predict with remarkable accuracy. Other times the universe throws us curveballs, reminding us of the limits of our knowledge. Yet, the pursuit of predictability continues to drive scientific exploration. It keeps us asking questions and seeking answers in our relentless pursuit of knowledge. The pendulum's predictable swing, a simple starting point. The pendulum, a seemingly simple object, embodies predictability. It swings back and forth governed by physics. With measurements, we can predict its every swing. We determine its period, the time for one full swing. This predictability makes it valuable. Used in clocks for centuries, its regular motion measures time reliably. When predictions get messy, the challenge of multiple objects. Predicting the motion of a single pendulum is relatively straightforward. But what happens when we introduce more objects? Imagine a system with multiple pendulums, their strings intertwined. Suddenly, the predictions become much more complex. Each pendulum influences the others. The interaction between objects adds layers of complexity. The motion of one object affects the others, creating a cascade of effects. This is where predictions become incredibly difficult. Even small errors in our initial measurements can multiply over time. Consider a simple example: a brick dropped onto a pile of other bricks. Predicting where each brick will land is a daunting task. The initial conditions of each brick, their shape, and even the slightest variations in the surface they rest on, all play a role. These complexities are not limited to the macroscopic world. The behavior of individual atoms and molecules is governed by quantum mechanics. Predicting the interactions within a system of billions of these particles is a formidable challenge. Why accurate predictions matter from bridges to rockets. The ability to make accurate predictions is not just an academic exercise, it has profound implications for our world. Engineers rely on physics to design safe and reliable structures. From bridges to skyscrapers, accurate predictions ensure stability and prevent catastrophic failures. In aerospace engineering, predictions are critical. Launching a rocket into space requires accounting for countless variables. The Earth's rotation, atmospheric conditions, and the rocket's own propulsion system all influence its trajectory. Even a tiny miscalculation can have disastrous consequences. Weather forecasting also depends heavily on physics-based models. Meteorologists use complex simulations to predict atmospheric conditions. While weather predictions have become increasingly accurate, the chaotic nature of weather systems still presents challenges. Accurate predictions underpin many aspects of our lives. They enable us to navigate the world safely, develop new technologies, and understand the universe around us. The quest for better predictions drives innovation and pushes the boundaries of our knowledge. Section 5. Enter the simulation, a powerful tool for physics. Faced with the complexities of predicting complex systems, physicists have turned to simulations. Simulations create virtual versions of real-world systems. They allow us to study and manipulate these systems in ways that are impossible in the real world. Imagine building a virtual bridge and subjecting it to various stresses. Simulations allow engineers to identify potential weak points and optimize the design before construction begins. This can save time, resources, and even lives. Simulations are particularly valuable in situations where real-world experiments are impractical or dangerous. For instance, simulating nuclear detonations helps scientists understand their effects without the devastating consequences of a real explosion. The rise of powerful computers has revolutionized the field of simulations. We can now create incredibly detailed virtual environments. From the movement of galaxies to the behavior of individual cells, simulations offer a powerful lens through which to explore the universe. Section 6. How simulations work. Building virtual worlds. Simulations work by representing real-world systems with mathematical models. These models incorporate the laws of physics that govern the system's behavior. By inputting different initial conditions, we can observe how the system evolves over time. For example, in a simulation of a galaxy, the model would include the gravitational interactions between stars and gas clouds. By running the simulation forward, we can observe how the galaxy's structure changes over millions of years. The accuracy of a simulation depends on the quality of the mathematical model and the precision of the input data. Even small errors can lead to significant discrepancies over time. That's why scientists are constantly refining their models and seeking more accurate data. Despite their limitations, simulations have become indispensable tools in physics. They allow us to explore complex systems, test hypotheses, and make predictions that would be impossible otherwise. As computing power increases, so too does the potential of simulations to advance our understanding of the universe. Section 7. Simulations in action, from buildings to quantum particles. The applications of simulations in physics are vast and varied. In structural engineering, simulations are used to test the stability of buildings, bridges, and other structures. They help engineers identify potential weaknesses and design structures that can withstand earthquakes, hurricanes, and other extreme events. In astrophysics, simulations are used to study the formation and evolution of galaxies. They help us understand how these massive structures formed from the early universe and how they continue to evolve over billions of years. Simulations also allow us to study phenomena like black holes and neutron stars, which are impossible to observe directly. Quantum mechanics, the branch of physics that governs the behavior of atoms and subatomic particles, relies heavily on simulations. These simulations help us understand the properties of materials, the behavior of light, and the fundamental forces of nature. Section 8. Can we simulate the brain? The ultimate frontier. The human brain is arguably the most complex object in the known universe. With billions of neurons connected in intricate networks, the brain is responsible for our thoughts, emotions, and consciousness. The possibility of simulating the human brain raises profound questions about the nature of consciousness and the limits of technology. While a complete simulation of the human brain is still far beyond our capabilities, scientists are making progress. Researchers have created detailed simulations of small sections of the brain, allowing them to study how neurons interact and how neural circuits function. These simulations could one day lead to breakthroughs in our understanding of neurological disorders like Alzheimer's and Parkinson's disease. They could also pave the way for the development of artificial intelligence that rivals or even surpasses human intelligence. Section 9. Consciousness in the machine, a philosophical dilemma. The prospect of simulating the human brain raises a fundamental question. If we can create a simulation that perfectly replicates the brain, would it also be conscious? This question has no easy answers and has been the subject of much debate among philosophers and scientists alike. Some argue that consciousness is an emergent property of complex systems and that any sufficiently complex simulation would inevitably become conscious. Others believe that consciousness is unique to biological systems and cannot be replicated in a machine no matter how sophisticated. The question of consciousness in simulations is not merely a philosophical curiosity, it has practical implications for the development of artificial intelligence and our ethical responsibilities towards intelligent machines. Section 10. The future of simulation, unlocking new possibilities. Simulations have become essential tools for physicists, and their importance will only continue to grow in the future. As computing power increases and our understanding of the universe deepens, we can expect even more sophisticated and accurate simulations. These simulations will allow us to tackle some of the most challenging questions in physics, from the nature of dark matter and dark energy to the origins of the universe itself. They will also drive innovation in fields like medicine, materials science, and artificial intelligence. The future of physics is inextricably linked to the future of simulation. As we continue to push the boundaries of what is possible, simulations will play an increasingly important role in shaping our understanding of the universe and our place within it. Section 11. Conclusion, Simulations and the Ever-Evolving World of Physics. From the simple swing of a pendulum to the intricate workings of the human brain, physics seeks to understand and predict the behavior of the universe. Simulations have emerged as powerful tools in this quest, allowing us to explore complex systems and make predictions that would be impossible otherwise. As our understanding of the universe expands and computing power continues to grow, simulations will play an increasingly important role in shaping the future of physics. They will drive innovation, unlock new discoveries, and deepen our understanding of the cosmos and our place within it. The quest for predictability is far from over, and simulations will be at the forefront of this exciting journey.